Right, in the last video, I alluded to the fact that there are an infinite number of solutions to these trig equations. But in problems 1 through 8, we were focusing on only finding solutions that were on the unit circle. So just values between 0 and 2 pi. So we're making a slight change in problems 9 through 16, and that is stated here in this first sentence. Find all solutions for theta in radian measure. Which means instead of just finding those solutions that are on the unit circle, I'm going to find an equation that would get me any of the infinite number of solutions that would solve this thing. And the process is actually very similar to what we did when we were just looking for solutions on the unit circle. In fact, if we want to find all solutions to a trig equation, the start is just finding all of the solutions that exist within just a single circle. So I'm still going to start by finding my solutions that are between 0 and 2 pi. So in example 1, solve for sine theta minus 2 equals 0. End up getting that sine of theta is 1/2, which means that I have solutions in quadrant 1 and 2. And those angles are pi over 6 and 5 pi over 6. All of that is still the same as we just did. Now, though, I want to find all other solutions. And those other solutions are going to be any angle that has the same sine value as either pi over 6 or 5 pi over 6. Which means I'm just looking at finding any angle that's coterminal to pi over 6 or that's coterminal to 5 pi over 6. So to find all solutions, I'm just going to add 2k pi to the solutions that I find on the unit circle. So my two general equations for solutions to this trig equation are that theta is equal to pi over 6 plus 2k pi, or theta is equal to 5 pi over 6 plus 2k pi, where k is any integer. All right, if we take a look at problem 2, this time we've got the cosine of 15 theta is equal to 0. Plus we're adding even one more new element. So in every other equation we've looked at, we've just had sine of theta equals something or cosine of theta equals something. This time, though, we've got a coefficient on the inside of our trig function that's attached to theta. So I've replaced 15 theta with x for just a moment to solve cosine of x equals 0, and then that's pretty straightforward from the unit circle. I know that that happens at just two angles, pi over 2 and 3 pi over 2. So I'm going to say that x is equal to pi over 2 or 3 pi over 2. But since I simply replaced 15 theta with x, I can just substitute 15 theta back in and say then that 15 theta must be equal to pi over 2 or 3 pi over 2. Move over to the right, and I'm going to set up my two equations again. Now that I've found my angles that are on the unit circle, I'm going to add that 2k pi to each one of them so that I have all coterminal angles to pi over 2 and 3 pi over 2. And now I simply need to solve for theta, which means dividing 15 to both sides. So this will be pi over 30 plus 2k pi over 15. And in the second equation, theta looks like it'll be pi over 10 plus 2k pi over 15. Since 3 over 15 can simplify to 1 over 5, which is why I end up with pi over 10. And then those two equations are all solutions to that original equation of cosine of 15 theta equals 0. In problem 3, I've got the 2 times the sine of 7 theta is equal to the square root of 2, which means that sine is equal to root 2 over 2. So 7 theta must be pi over 4 or 3 pi over 4, since I need angles that are in either the first quadrant or the second quadrant, since that's where sine is positive. So I get starts of my 2 equations. 7 theta is equal to pi over 4 plus 2k pi to get all coterminal angles to pi over 4. And I'll do the same with 3 pi over 4. Add 2k pi to get all angles that are coterminal to it as well. So notice that I'm adding the 2k pi before I divide by 7, since I know that really the angle that's being plugged into sine is 7 theta. So I want to add that 2k pi before I divide the 7, because this time it's the whole quantity of 7 theta is what we'd consider our angle that we're plugging in. So I then want to solve for theta, which means dividing both sides by 7. So pi over 28 plus 2k pi over 7. And in the case of our second equation, this will be 3 pi over 28 plus 2k pi over 7. And those 2 equations are my solution. All right. Problem 4, we're going to be mixing a couple of pieces together from the previous set of problems. So I first have a quadratic equation that's 4 sine squared plus 3 sine minus 1 is equal to 0. So step 1 is to factor that quadratic equation. I end up getting 4 sine theta minus 1 times sine theta plus 1. Again, if factoring a quadratic trigonometric equation is not your jam, just change sine back to x and factor 4x squared plus 3x minus 1. And you should end up getting a similar result. And then you can substitute sine theta back in. But then I'll use the zero product principle to separate those factors to say that 4 sine theta minus 1 is equal to 0, or sine theta plus 1 is equal to 0. So let's start with the right side of that equation, because that's the easier route, I think. We end up getting sine theta is equal to -1. So I get just one solution on the unit circle there, and that's 3 pi over 2. Cool. On the other side, though, I end up getting that sine theta is equal to 1/4, which is not a value we know from the unit circle, so we're going to need to use a reference angle. So sine is equal to a positive number, which means I'm looking for solutions in quadrant 1 and quadrant 2. I'll get that reference angle by taking the sine inverse of 1/4, and I come up with a value of 0.2527. And then I'll move up to this upper right corner. Well, now I know that I should have a solution in quadrant 1 and in quadrant 2. In the first quadrant, it's just the reference angle. In the second quadrant, my angle should be pi minus the reference angle, and I get those two numbers, 0.2527 in quadrant 1 and 2.8889 in quadrant 2. So now that I've gotten all my solutions that are just within the unit circle, I'll do the same thing that I've been doing, where I just find all the coterminal angles to them. So I had 3 pi over 2 was an angle. I had 0.2527 was an angle rounded out to 4 decimal places, and 2.8889 was another angle. And then add 2k pi so that I get the coterminal angles to each of those 3 angles. And then those 3 equations together make up the entire solution set to that trig equation. All right. Problem 5, we have a similar thing going on as we did in problem 4, where again there's a quadratic equation, but also I have a mix of two different quadratic functions. I have cotangent squared minus 3 cosecant is equal to 9. So since I've got two different trig functions, my first step is going to be to use a trig identity to get rid of one of those trig functions, so that I can focus on having just one trig function instead of two in my entire equation. So I'm going to use a Pythagorean identity on cotangent squared, which is that piece then that's written in blue. Cotangent squared is equal to cosecant squared minus 1. And then I'll combine like terms in that second line. I have a minus 1 and a minus 9 after I move the 9 to the left side of the equation. So I have cosecant squared minus 3 cosecant minus 10 is equal to 0. So once again, I'll factor that mess. Get cosecant minus 5, and cosecant plus 2. And if we look to the right side again, focusing on cosecant theta plus 2 equals 0, I end up getting that cosecant theta is equal to negative 2, which has two solutions that we know from the unit circle, 7 pi over 6 and 11 pi over 6. Since keep in mind that cosecant is 1 over sine, so if cosecant of theta is equal to negative 2, that means that sine of theta is equal to negative 1/2. And that's something that we can solve pretty easily from the unit circle. So if cosecant theta equals negative 2 is not your jam, just change that over to sine theta equals negative 1/2, and then you should be able to solve just based on the unit circle. All right, then we'll come back over to the left side. Right here, cosecant theta minus 5 equals 0, meaning that cosecant theta is equal to 5, or sine theta is equal to 1/5. Not a value that we know off the unit circle, so again, we'll need a reference angle. And that reference angle is the sine inverse of 1/5, which comes out to 0.2014. And since sine is equal to some positive number, I'll again look for solutions in quadrant 1 and quadrant 2, which is what's up here in the upper right corner. In quadrant 1, I just want the reference angle, and in quadrant 2, I want pi minus the reference angle. And I come up with those two numbers listed there. So all of that was just solving this equation within the unit circle, just like we did in problems 1 through 8. So now I'll aggregate all of my solutions. 7 pi over 6, 11 pi over 6, 0.2014, and 2.9402, and then add 2k pi to each one of those to get all solutions for theta. Since anything that's coterminal to one of these four angles on the unit circle is also going to solve this trig equation. All right, that's probably about as messy as it gets. Here we have problem 6, where we're going to change what we're solving for slightly. Because we're actually going to go back to the same equation that we were asking in the first set of problems in 1 through 8, where we're back to looking for solutions for theta in 0 to 2 pi. But there's a bit of a twist this time, because I'm going to be adding that coefficient to theta back in. So it turns out in order to solve this kind of equation, where I might have cosine of something like 3 theta is equal to 0.5, I'll actually need to start by finding these solutions between 0 and 2 pi, then find the general equation for all solutions, and then find specific values from that general equation. So if problems 1 through 8 had 1 step, then problems 9 through 13 had 2 steps, then these last few problems, 14 through 16, all have 3 steps. So like we've seen before, we get that 3 theta is equal to pi over 3, or 5 pi over 3, since keep in mind that 0.5 is the same as 1/2, so that is a value we know from the unit circle. So we're looking at quadrants 1 and 4 to get pi over 3 and 5 pi over 3. Over to the right, and we'll solve each of these pieces for theta. So 3 theta equals pi over 3 plus 2k pi, divide 3 to both sides. And then I took the extra step over here to combine my 2 fractions into one common denominator. So I ended up with pi plus 6k pi over 9, since 9 would have to be my common denominator. I do the same thing for the other equation and end up with 5 pi plus 6k pi over 9. And now I want to turn my attention to actually solving for all values of theta that are between 0 and 2 pi. So all values that are just within the unit circle. And I'm going to need these general equations to do it. So that means I'm going to pick specific values for k. And since I was looking at the cosine of 3 theta, I'm going to end up needing 3 values for k. And we're going to start at 0 rather than starting at 1, which means whatever coefficient I have on theta, I'm going to use every whole number up until that 1. So I'm going to use every whole number up until 3 for k. So 0, 1, and 2, but again, it's 3 values for k because it's 3 theta. So we'll come down to this table where I'm going to be plugging in 0 and then 1 and then 2 into each equation for k. Those equations being pi plus 6k pi over 9 and 5 pi plus 6k pi over 9. So in the case of 0, I get pi plus 0 over 9, which is just pi over 9, and 5 pi plus 0 over 9, which is 5 pi over 9. Move into that next column, and now I've got k equal to 1. So I'll get pi plus 6 pi, which is 7 pi over 9. And below, I get 5 pi plus 6 pi, which should be 11 pi over 9. And then in that third column, plug in 2 for k, which means I'll get pi plus 12 pi over 9, which should be 13 pi over 9. And then in that lower right piece, 5 plus 12 is 17 pi over 9. And those 6 solutions in green make up all angles theta between 0 and 2 pi that solve the original equation. So in general, whatever coefficient I have on theta, I'm going to find that many solutions for every general equation that I have. So in this case, I had 2 general equations and 3 theta, so 2 times 3 is 6 equations, or 6 solutions, not 6 equations. All right, in that next problem, I have that the tangent of 2 theta is equal to the square root of 3, which means that 2 theta is equal to pi over 3, or 4 pi over 3. Bring that over to the right side, and I'll solve each of those equations. And then we'll also get a common denominator, getting the equations pi plus 6k pi over 6, and 2 pi plus 3k pi over 3. So come back to the original equation. I had tangent of 2 theta, which means that I'm going to look for k being equal to 0 and 1. So I should have 2 values for k because I had 2 theta. So in practice, I'll just plug in 0 for k in my 2 equations and get pi over 6 from the first equation and 2 pi over 3 from the second equation. And then plug in 1 to get 7 pi over 6 in the first equation and 5 pi over 3 in the second equation. Right. Then bring that into our last problem. Cosine of 4 theta is equal to -1, meaning that 4 theta is pi. So theta is equal to pi plus 2k pi over 4. So this time I only had one angle that I had to solve for. I mean, I'll only have one general equation, but we'll make up for that by the fact that I have 4 theta, which means that I'm going to have 4 values for k. 0, 1, 2, and 3. Because once again, I'll go up to the whole number just before my coefficient on theta, since I'm going to include 0 for k instead of 4 for k. So I'm going to starting at 0. So bring my equation down. Theta is equal to pi plus 2k pi all over 4. And I'll plug in my 3 values for k. At 0, I get pi over 4. Add 2 to get 3 pi over 4. If k is 2, I'll add 4. Then k is 3, I'll end up adding 2 again. So 7 pi over 4. So notice that each time I'm just adding 2 pi over 4 to get from number to number, or angle to angle.